Okay, let's take a look at what it takes to actually implement one of these sidechain tokens. And this is in the notes so that you can go get this code and use it yourself. It's going to be checked in where you'll have access to it, but we're going to build some of these things and test them. There are a number of pieces. This is Ethereum code. It's done in Solidity. Ethereum has an underlying machine language that this compiles to. So there is an Ethereum virtual machine. And Solidity is not the only language that you can use, but it is like 90% of the time this is what you would use for Ethereum. There is supposedly also a very close to production-ready version of Ethereum to run for the Cardano chain. Or not Ethereum, but a very close to production version of Solidity for the Cardano chain. So you'll be able to use these contracts on multiple things. You can also compile Solidity code to run in IBM's Hyperledger, which is a permissioned blockchain environment. Okay, so the first thing in Solidity, and some of this is going to be this is how Solidity works stuff, is this pragma. You can compile things at different versions of the compiler. Unfortunately, at version 6, the syntax of this pragma changed. So this is the new syntax for what this pragma looks like. But the pragma says you're using Solidity, it has to be between these versions. And Solidity has gotten a lot better in the past year. They've quit making breaking changes to the language. So this pragma is actually working now, whereas before it wasn't really working the way you would want it to. The second thing is this import. I'm using the Open Zeppelin library. Why would you want to use a library like this? Because smart contracts are subject to all sorts of security problems and concurrency problems, and these are the kind of things that get worked out when you have a security audit for the contract, and Open Zeppelin has been security audited. A security audit for smart contracts costs hundreds of thousands of dollars. So being able to use an underlying library that's already been security audited makes it vastly easier for you to build something that you can be certain works right. Now that means you have to understand the underlying library, and that's one of the things we're going to get to here in a minute. I have a comment. Normally the comments in Solidity, you can start with 2 slashes to the end of line or /*. It works like C code. Everybody uses a couple different documentation tools. This is based on a tool called Oxygen to be able to produce clear documents from the code as to what the what is in the code. So I followed the Solidity coding standards, and I've used this format for the comments. Now, Solidity is an object-oriented language based on tokens, or on objects, and the top-level object is a contract. It has a name, in this case, example token. You will find with the other tools that we use, especially Truffle, that pretty much if you have the example token contract, you have to put it in the exampletoken.sol file. And you have to get the case and the spelling right. If you don't, it will break all sorts of stuff. And it also means that you only get to put one contract in each file. It inherits from erc20. erc20 is the thing that we imported up here. You'll notice that it was called erc20.sol. That contract is specified in there according to a standard interface specification in the language. And anybody can implement a different implementation of an erc20 provided it meets the interface specification that is in there. So if you've got a better way of doing it, get prepared to pay your $100,000 to do a security audit or 200 and go to it. There's the opportunity. You don't have to use their code. But this is, most people that are going to do this is what they use. It has a constructor. Now, constructors, when you think about it, you think about when the data gets instantiated, the constructor gets run. In the case of Solidity and Ethereum, when the contract is created in the chain. You take it, you compile it. There is 2 pieces from the compilation. There's a binary and there's an interface to the outside world. Then you load it onto the blockchain, and when it gets loaded, it gets an address. Okay? That address is important, And it's really important when you load a contract that you know what that address is and you know what account was charged for loading the contract, because that account is the owner of the contract. But at the point in time when it gets loaded, that is when the constructor gets run, not later, which means that all the things that you want to initialize are fixed at that point in time. So this constructor gets called from the outside world. In this case, it's past initial supply, and it says that it is a public contract. There are a whole bunch of special operations like restricted and public and stuff like that. And then it calls the underlying constructor, which is what it's inheriting from. This is erc20, and it passes it a name of example token and a symbol, and then it turns around and does whatever initialization it needs to do. And in this case, it calls something called mint. Mint creates tokens. And it says, I want to create the initial supply of tokens. And that initial supply, you could say there's 100 tokens or 100 million, whatever it is. You have lots of choices in this. I didn't specify the number of decimal places. It's 18. But the numbers, the integers, are 256-bit integers in this language. So they are large. Unless you specify otherwise, that's what you get. And for things that are stored, like the initial supply, it's always a 256-bit integer. You don't have a choice. And then there's this other thing called message sender. Now, the message sender is the person who's creating the contract. The message is the transaction that creates this contract and writes it onto the chain. There are a whole bunch of different things that can be in message. Some of them are available at the beginning of a transaction, like the sender. Some of them are not available until the end of a transaction after the transaction is completed, like the total transaction cost. But we can look up and get a list of the available things in the message, and there's a number of them. And message sender, it turns out, is really important because inside the contract, remember, we only wanted Intel to be the one that could mint Intel stock. Well, then the contract has to save who Intel is. That's the message sender. It's an address. And whenever the mint gets called after this point in time, the actual mint call, not the internal mint one that we're doing inside the constructor, but suppose we want to add another 100,000 stock, then that add stock thing has to say, is the person making this call the message sender that I got from the constructor? And that's how you implement the security. That's the simplest layer of security. And there's actually other layers that are already built into this so that you can have roles where you can grant specific accounts different roles. But this is the simple layer of security. And it calls this internal function called mint that is actually not public. It's only available to other things inside this derived contract. Okay? And then it's done. It's using the standard erc20 interface. There's no extensions. There's no, delayed turn off or any of the other options. We could have those things. We could inherit from multiple things up here, and there are other options, but this is just the minimal erc20. It's a very simple erc20. And it's used basically all the defaults. Now, if you looked at this contract and you say, what does it do? You would have to go digging through what is the set of things that is an erc20 contract. And for this particular token, I went up here and I made a table that lists what these things are. And I hope most of the descriptions are kind of self-evident, but we're going to walk through what these different things are inside this contract, and we're going to talk about them in some detail so that you have an understanding of what is an ERC20 contract, what is an ERC721, what is an ERC115, how do they differ, and how do you use them. These cover a pretty broad spectrum of financial instruments when you get down to it. So we're going to look at a bunch of others, but right now, I just kind of want to walk through these things and say, this is what it is, and this is what they do. Now remember, when you do an initial offering, quite often you have to approve who's going to buy stuff. And consequently, this approval takes the address of the owner, a spender, and a value. And that value is they're approved to purchase something at a particular price, basically. There's an initial supply. Remember when we created it, we said we're going to have 500,000 or something. That initial supply is, it's zero parameter function returns. That's how many were created in the contract at the beginning. And if you then later come along and mint that, or mint more, that would show up as part of the initial supply the way the contract is implemented. But some contracts don't allow minting. Some of them are fixed. You can't mint. Some of them allow getting rid of things. You can burn them. So this initial supply is how many is total in the entire system available. Now, not all of those may be owned by the initial owner, but that is, what is the total number? And, if you look at Dell Foods and they had 1/3 more than their total number, with a smart contract, you don't get that problem. You just look at the initial supply. That is what it is. Transfer takes a from address and a to address. And how many? That transfer is how many units can you send, or are you sending from one person to another? Now, of course, the from person has to have enough units to send. You can't make it go negative. There's a special math package called Safe Math that under the covers ERC20 uses that guarantees some of these things like that. If you get a negative number under that circumstance, it will automatically error and it won't allow the transaction to complete. It'll roll it back. Allowance. We'll come back to a couple of these. Approve is how you approve a particular spender to have a particular number or how many they have left that they can acquire. Balance of is how many you have now. So if you're the person Bob and you bought 100 and later you bought another 100 and then you called balance of on this contract to see how many you have, you'd get back 200. Decimals tells you the fractional unit, and you notice that this actually returns a uint8 as opposed to one of these standard 256-bit uints. Solidity has every data type size from uint8 all the way up to the 256-bit value. And you can return these things. Not all languages support this. It would convert it to a larger number. So if you have a Python interface into Ethereum, you will find that this function doesn't return a uint8, it returns an int. But it is an unsigned 8-bit integer is what it's returning. Now, the number of decimals tells you how much the fractional portion can be. Like in United States dollars, we have 2 would be the number of digits of fractional stuff. In lots of stock thing, we look at things in terms of 3 digits, or bonds have a 3-digit discount rate. Okay, so it depends on how many decimal places. The default for these things is 18 decimal places, which is a lot of decimal places. And that's just basically a return function. It doesn't take any parameters. You can't change it. It gets set when the contract gets built. But you can ask the contract how many it is. Now, you'll notice that here we have an increase approval, decrease approval, which goes back here with what your allowance is for your approval and your approval. But all of those things are to allow you to control who can buy and how much of your initial offering. There is a name. Again, you notice no parameters, which means it returns the name of the string, which in this case is going to be example token. There is a symbol, same sort of thing. It returns the ETX. There's a total supply. Now, this initial supply refers to how many you have minted. The total supply refers to how many are currently available. And that total supply available is how many the owner owns at the current, the owner of the stock, not how many outstanding ones there are, but how many do they have available that they could actually sell. Now, transfer down here is, you'll notice that this is a transaction marked, which means it requires a transaction, and I'll explain the difference between the transaction and the const in this column here in a second. But it says at this point we're actually going to transfer to an address from the owner of the contract this many units, and it returns true or false whether it could do that. Transfer from is the opposite operation that takes stuff from, and it also has to be transaction signed. Both of those require that you be the owner of the contract, or in the newer model that you have the approval to call that. You have a role that allows you to call those things. But this is basically how things get transferred. Now, if you are a secondary owner, as in you're not Intel, you're Bob who bought 500 shares, then you can transfer to somebody else up to 500. That's your value over here of these items. So, and there's the constructor, which you saw down here. You'll also notice there's an error in my program. I will go find that because it should list that there is a parameter there, but it doesn't for some reason. I will fix that before you guys get a chance to ever use that program. Now, across all of these, this makes the simplest interface for an ERC20. It's the minimal interface. You don't see burn, you don't see mint, you don't see any of the other options. There's things like being able to pause transfers and unpause transfers. There's a whole bunch of other things we could do. But this is the basic, simple interface for this that is underneath the inheritance of ERC20 right there. And this is what you get as an ICO. You may want some of these other things, and you may want to plan ahead for some of these things. Now, the const ones, the Ethereum network has about 12,000 nodes in it. And any one of these nodes could make a call to create a transaction to do something across the entire network. But every one of these has the past data themselves. So these ones that are listed as const, those are ones that return from the local node. They don't require a transaction, which means basically they're free to call. You can find out the name, you can find out the symbol, you can find out the total supply. All of these things are local read-only data operations. Now, when you actually want to approve somebody or you want to make a transfer, a sale, that's something that has to be reflected in every node because you're changing data across the entire network. That has a transaction. The transaction takes an amount of money to pay for to make that transaction happen. And at the end of it, when the transaction is run, you should have a transaction receipt, and you'll know whether or not it succeeded or failed, and that tells you that you actually made the transfer successfully. So these ones that I've marked with TX, those require additional parameters. And those additional parameters is, yes, you have to spend some money. It has to come with an account and an address for that account. And when you get done, you've changed the state of the entire Ethereum network. Now, the reason why I wanted to do this before we did the client server and the wallets is because here we are with the security question is, how do we determine if we have a transaction? And the answer to that is your transaction has to have a signature that says it's you, it comes with this account, your account has a certain number of tokens in it, and you are willing to spend tokens to make this happen. So when you start looking at smart contracts, suddenly you realize, yes, some things are just constants, like how much is in an account. And that's like looking up in our index what is in an account and then going and summing it up. And you get a return value. That doesn't require changing anything. Those are constants. Some other things require that you actually spend tokens to make it happen. You're paying for an action. And those are the ones that we'll look at in terms of signatures. The simplest transaction in existence is one that just does a transfer. We implemented the transfer stuff in Homework 3. We're going to implement the signature part that we kind of skipped over in Homework 4. So here's the motivation for the signature. And before I get off of this, we're actually going to take this contract and build it and test it. I mean, here's the code. This isn't much of a build, but this is like our Hello World contract. Because when we get to a tool called Truffle, Truffle is a local copy of Ethereum, and this is what most people use for development for Solidity. It has, when you install it, you get a Solidity compiler. The Solidity compiler, we've got to do some configuration to get it to work for what we want. We'll walk through that, and we'll actually poke into, here's how you build a smart contract, here's how you test it, here's how you call the constructor with initial values, and then we'll be able to tie that to some kind of a front end with a thing called web3.js. So here's our first contract. We're going to get back to this about, I think, assignment 6 here in a while. Okay? But yeah, this is where our first contract is. It may be assignment 5. That's coming up. And I'll send you this code again. I'm not hiding it. I'm not going to make you look it up again on how to use it. If you look at the notes for today, it also includes all the things that get inherited that make all of these other things work up here. And it's worth taking a glance, and I do mean a glance, don't study it. Take a glance down through it and say, oh, I see code, I see there's multiple contracts, I see, pieces. But basically, this is your simplest one. If we want to get most of the other pieces, we just add multiple inheritance in here, and then we start overriding things in those contracts with our own implementation. And we can add to, here is our entire set of behavior and what we're testing. This is a mutable token. I think I mentioned that before. And mutable means they're interchangeable within each other. All that it's keeping track of inside the smart contract is the owner and the quantity. It isn't keeping track of any other information. So basically, you're creating a table out there on the network that says, this owner owns this many, this owner owns this many, and some security and a process around that allows you to trade, approve, transfer these different things. And that process around it is what we call a smart contract. And as you can see, this isn't necessarily a hugely complicated piece of code or a hugely complicated process. And the entire contract and what it's building is several hundred lines of code, even with all the things that are coming in as from the Open Zeppelin library. It's not complex. It is difficult to make certain that you have tested it and get it to work right. We're going to walk through how you test stuff and how you pay for running contracts, how you pay for loading contracts, and how they perform. And also, one of those important things is in the Ethereum network, you pay for running contracts on a language that is derived from JavaScript, and it's a Turing complete language, which means that you're not guaranteed that anything completes. It is a general purpose programming language, as opposed to the language that goes into something like Cardano, which is this language, Marlow, and that's IOHK's or IO Global today, their language. And that is not a Turing complete language, but it gives you all sorts of proofs and capabilities that, yes, at the end of running, all of these things are true. All right. With that, we'll catch you later.